welcome to whatever month this is. I think it's still August edition of Spacecraft. We have a few announcements before we get started. Announcement number one, tip your bartender. There's also a food truck outside if you want food, and it will be here throughout the night. So when we have an intermission between talks, you're certainly welcome to go out and get more food if you want it. Also, we are near train tracks, and so what that means is that sometimes a train will come by and it'll get pretty loud in here, so you can't hear the speaker. And for those of you that have been here before, you know that the sort of tradition tends to be that the speaker will raise their glass and say choo-choo, and then you'll take a drink while the train's going by. We also have several cool events coming up aside from our cool talks today. Next week, if you've heard in the news, the OSIRIS-REx mission is going to be launching from Florida, Cape Canaveral, and there's actually going to be a live event here to watch it. It will start at 3:30. The launch itself is around 4, so if you're going to watch it, you want to make sure you get here not super late, because then you're going to miss it. And after that, there'll be a talk by Eric Christensen, who's the director of the Catalina Sky Survey, to talk about the science of the mission and how we discover asteroids here in Tucson. I think with that, we can go ahead and get started. With that, our speaker for today is going to be, our first speaker is going to be James Keane, and he is a graduate student at the Lunar and Planetary Laboratory at the U of A. And aside from studying gravity on pretty much every single body in the solar system, he also is a very good graphic designer. The shirt that I'm wearing right now is designed by him. All of our logos, our spacecraft logos, are designed by him. And I think actually both speakers have designed t-shirts, so both of them are pretty good in design. And with that, I'll go ahead and get started. James, do you want to come up and talk with your dog? Okay.
This is cheesecake. This is my excuse why if any slides break or weren't finished. Or weren't finished, it's Cheesecake's fault. So here, I'll let Okay, so am I loud enough back there? People hear me? Okay, hopefully. So I'm going to talk a little bit about the study of the lunar gravity field, which seems kind of odd, but it's one of the big results from a small little NASA mission called GRAIL, which I've been a part of for the last 3 years. And so here's, if you've been watching, this is a little spinny GIF, or GIF, whichever way it goes. Is this loud? Like right into them? Okay. Okay, so we're going to look at the moon's gravity field. If you've been watching for the last few minutes, up here is a spinning animation of the moon. This is actually not real images. This is based on data from a spacecraft currently orbiting the moon called the Lunar Reconnaissance Orbiter. But we're going to instead focus on a really specialized small mission that I've been a part of for the last few years called GRAIL, and it basically uses gravity to look beneath the surface of the moon and study the interior structure. So this is these colors now correspond to variations in the gravity field of the moon. And so you can see there's a lot different information, I should say, in this compared to the previous animation. So before I go on, why would you even care to study the moon? I'm sure you can't read anything on this, but this is a little clock of geologic time. Basically, the red-orange up on the top symbolizes the start of the solar system, the formation of the Earth. And as you go clockwise around this plot, you eventually get to today in that greenish, light green color. Now, on Earth, if you go outside and you look at the rocks outside, you go up into the Catalinas, usually you're going to find rocks that are very young compared to the age of the solar system. You're going to find things less than 1 billion years old. And if you want to study the origin of the solar system and also the origin of life, which is that purple line that goes around the edge, those are the first single cell, basically animals, and life began well before we have a good geologic record on the Earth. So why not go to the moon? The moon has almost no present-day geologic activity and is a great record of the early history of the solar system. And So if you want to study basically the formation of the Earth, the early solar system, the moon is great because it has that record and it happens to be right next door. This is an actual image from the Galileo spacecraft. It's looking at sort of an odd angle of the system. This isn't actually how far away the moon is from the Earth, but the relative size scales are correct. If the moon were that close, we would have some problems. So I've been told that you guys do questions and sometimes give out prizes. So I've already told you that these distances aren't quite the scale. But let's say I took the Earth, I stacked a bunch of copies of the Earth on top of each other. How many Earths would you need to go away to hit the moon? Or phrased a different way, how many Earths could you fit between the Earth and the moon?
Raise your hand if you're going to answer.
Raise your hand if you want to guess. Back there.
127.
127, no.
I guess too high.
30. Right there, that's the right answer to within one sig figs. So the moon is actually quite far away, even though it appears big in the sky to your eye. This is, again, another real image taken by the Mars Odyssey spacecraft on its way to Mars. And this is taken with just the right geometry, so that way the moon, you get sort of the furthest apart that they could be on the sky. And so you get both the apparent size and distance correct. So moon's 30 Earth diameters away. That's still very close on the cosmic scale. Makes it very easy to get to, and accordingly, we've sent a crap ton of missions to the moon. So this is a little cartoon made by the National Geographic, and it shows pretty much all planetary missions that we've ever launched.
Wow.
This point right here at the center is Earth. It doesn't include any Earth-centric spacecraft. The moon is this guy up here, which has the most spacecraft going towards the moon in the last 50 years. Over here you have Mars, and over here you have Venus. And then there's a whole host of other random things, like we occasionally send spacecraft to study the sun, Mercury, and every single outer solar system mission is these like 5 lines. So that means it's well studied. So what do we know about the moon? And perhaps most of this scientific knowledge, or a huge chunk of it, comes from, of course, the fact that we actually landed there, and we're able to study rocks in situ and better develop our understanding of the moon. And I can even ask another science question, because how many do I need to give away? 2 more, okay. We'll do one here. So this one is no prize. There's going to be 2 parts. The second part, there will be a prize. How many people have set foot on the moon? Way back there on the bar. I can't hear you. Someone way back there raise their hand, unless you're asking for a drink. Okay.
It should be 12.
12?
Right?
Lower. 7? Lower. They landed in groups of 2.
How 11, 12, 14, 15, 16, 17.
6. 12. 12. Okay, that's not a prize, although I should lose prizes for that. How many adults are scientists? That's my question. 1.
Yeah.
1 was a scientist. So we've sent astronauts to the moon, they've collected samples, but we've only ever sent 1 scientist, Jack Schmidt, on the last mission. He was a geologist. So I guess Sandy, you get a prize. That might be a little cheap. She works in our department.
That's cheating.
So, and this is actually Jack Schmidt, a picture of Jack Schmidt right there on Apollo 17. So that's where we've got a good chunk of our information, but we still send missions today. This is a picture of the lunar, or a graphic of the Lunar Reconnaissance Orbiter that is currently there now. And we get a whole host of information from these orbital missions, including this graphic I showed at the beginning. Yes?
How long's the LRO been there?
LRO has been there, oh gosh,
Seems like it's been a while.
Longer than I've been in grad school.
longer than Sarah's been in grad school. I want to say like 6 or 7 years.
Oh, okay. Seems like, yeah.
It's been there a long time, which is, it's actually a testament to the mission. Is the LRO and many other NASA missions are designed for really short windows, but they're over-engineered and they will end up lasting oftentimes much longer than they're intended. But LRO produced this graph, or produced the data set that enabled me to make this graphic. So this is showing basically the color on the surface, or how bright the surface is. And so you see all sorts of different structure here. You see these dark regions. These are the mare. They make the face of the moon if you go out and look at the moon. They're basically lava flows. But you can also get all sorts of other information from orbiting. This is topography, so that's a measure of elevation. Blue in this map means it's a lowland, like a valley you can think of. Reds are highlands, like mountains. And so you can get other information that you can't get from just looking. And the way that they actually measure this is the LRO spacecraft has a laser, and it bounces lasers off the surface of the moon and measures the time it takes for the lasers to come back. And so you can get information about elevation. You can also look in other wavelengths of light. This is a map of temperature on the moon as measured from space. This is measured by, or derived from an instrument called Diviner, and it measures the infrared radiation, basically a measure of heat coming off the surface of the planet. You can see the equator is hot here in red. As you go towards the poles, it gets progressively colder, and there are actually some very tiny regions that you can't even see on this plot that are cold enough to have water ice stable at the surface. And that's been an intense focus and research for lunar science in the last 20 years or so. And you can also, even though you can't land and do geology in situ, you can get information about the chemistry of rocks from orbit. This is a map of thorium, which is a proxy for sort of radioactive isotopes. And you can actually see this big blotch of red, yellow. We'll come back to that later, but that's associated with all those volcanic outflows that we can see if we look at the moon and see all the dark patches. And so you can get all sorts of information just from looking from orbit. But if you really want to get what's going on beneath the surface, you need other techniques. All these techniques only probe at most the top meter. So you're only looking, if I'm sort of, the surface of the moon is up here, you're only looking down to about my waist. That's not a lot of the moon. If you want to get beneath it, one great way to do that is gravity. So here's the little bits of slides I've stolen from some classes I do do outreach for the astronomy camp that Stuart affiliated, showing how does gravity work. So right now, you're being subject to gravity of the Earth. And I forgive you, I showed an equation, it's not really important. But of course, you're not flying off into space, you're effectively falling down towards the planet at any given time. And how strongly you're being pulled towards the planet depends on the amount of mass inside the planet. So the Earth, there's more mass in the Earth, it pulls stronger than if you were, say, standing on the surface of the moon, which is why astronauts can jump and bounce around on the moon. Now, if it's a perfectly spherical planet, that surface gravity is constant everywhere. That 9.8 meters per second squared that you may or may not remember from high school. But in reality, there's this pesky thing called geology, and it makes the surface of the moon or the Earth bumpy. There's all sorts of geologic structures, and I'm sorry my dog is whining in the back. And so here I've drawn a little cartoon of someone walking towards a mountain. And normally you have, say, that 9.8 meters per second squared of acceleration towards the planet. But as you get closer to a mountain, you're actually pulled slightly stronger. And why are you pulled slightly stronger? It's because there's all this extra mass here. You basically increase that number, so you're being pulled downwards and also slightly to the side. And so if you can somehow measure this gravity, you can figure out, well, in this case, you've used a really stupid way to determine that there's a mountain in front of you. But it's useful for looking at things beneath the surface as well. So here we have some sort of like volcanic intrusion or ore body. This is commonly used for mineral exploration. That sometimes will show up as an increase or sometimes a relative decrease in gravity. As you walk over it, let's say you're walking over a big thing of nickel, the surface gravity will change, and you can measure that. One way you do that is a spacecraft. So if you have a satellite flying over the Earth, it has some velocity, it has some trajectory, and if there's an extra mass beneath it, that's going to change the trajectory. Basically, normally it's being pulled sort of straight downwards towards the center of the planet, but as it flies over this mountain, it's being pulled a little bit extra as it flies towards the mountain. It maybe speeds up as it heads towards this mountain. And as it flies away, this mountain is sort of tugging back on it, and it'll slow back down again. So if you can measure the speeds of satellites, you can back out what's beneath you, and back out the effect of gravity. And so on Earth, this is one way we do this, and it's actually oftentimes based on using GPS data and using other spacecraft. So if you have a nice big giant satellite dish on the surface, you can use that. You can measure all these velocities between different things. Now, if you go to a different planet, can you guess which planet this is? Doing this is a little bit harder. The gravity field changes because you have mountains, you have all sorts of other geology, but you don't have these nice big ground stations to measure everything. So it's red because it's Mars. This is a picture actually from the Indian spacecraft that's currently orbiting Mars. And so how do you do this around another planet? Again, forgive the equations, I use this for other purposes. So let's say we have here, this is a nice pretty picture of Mars, very pretty. And you have your spacecraft flying around Mars. As it flies around, it's subject to all these different poles from, say, mountains, volcanoes, other things on the surface. That changes its velocity, and we can measure that change in velocity basically along the line of sight. So if the spacecraft flies over a mountain, we can measure the change in sort of along the track to the spacecraft from Earth. And if the train comes by, this is one time I want the train to come by, I can show a demo of the Doppler effect. You'll hear, as the train comes towards you, you'll hear one pitch from the horn, and as it goes by, that pitch changes. So as things change velocity, here in this case the train is coming towards you and then it's going away, that is a change of velocity. You can measure that in that case with sound, and in this case with radio waves. Now, one complication, let's say your spacecraft is trying to measure this mountain on the far side of Mars. Your spacecraft will fly over it at some point if you picked your orbit right, but you no longer have line of sight. You can't see the spacecraft, so you can't measure the changes in its velocity as it flies over this mountain. So how do you deal with that on Mars? This can be a question. What would you do? I want to measure that gravity field on Mars. What do you do? Magic, that's right. A little bit simpler. Mars spins.
You wait till it's on the right side.
So if you wait approximately 12 hours on Mars, that mountain will eventually migrate onto the near side of Mars, the side closest to the Earth, and then you can measure it. And the spacecraft will fly over it. Now to the moon. Let's say we send a spacecraft. Sorry, question.
I'm just curious, in terms of the relative G of the planet, what's that differential in terms of, I mean, it's got to be like a fraction.
It's in tens of thousands
of a percent.
Thousands of a percent.
Wow, okay. It's pretty sensitive.
Yeah, so I don't have slides talking about that, but for GRAIL, which is really the gold standard of gravity missions, we measure the precision of that, the velocity precision of that spacecraft down to microns per second.
Wow.
So like a micron is like smaller than the size of a human hair. So we measure these changes in velocity extremely precisely, and that's what those measurements are what enable GRAIL to do what it can do.
That's impressive.
So back to the moon. So now the slides will be gray instead of red. So let's say we have a spacecraft flying over the moon. They can measure all these different gravity fields. But the big problem with the moon, unlike say Mars or any of these other planets, is the moon is locked and we only see one side of the moon. So if there's something interesting on the far side, your spacecraft will again fly over it, but it will never be between the spacecraft, that feature that you're interested in, and the Earth will never be in a line that connects up without going through the planet. And so before GRAIL, that meant, we'll look at, this is a plot of topography. Again, I showed a plot similar to this, but in nice, pretty spinny globes. Purple and blue are low-lying regions. Red is high-standing like mountains. This side of the plot, the right-hand side, is the near side, and the left-hand side is the far side. And this is a map, the bottom one is a map with the gravity. And one thing you can notice, even without looking at what is in this map, is on the near side, the gravity looks nice and sharp, nice and smooth. If you go to the far side, you all of a sudden get these stripes that go in all sorts of different directions. It's noisy, and that's because you couldn't see the spacecraft on the far side. So you can't really get at the gravity at the far side of the moon. So GRAIL comes at this in a different way than doing this sort of line of sight measurement. Instead of having one spacecraft, They have two. And so there's two spacecraft in the GRAIL mission, GRAIL A and GRAIL B. They are named Ebb and Flow. Which I don't think Mike Sorry is here, but I much prefer the runner-up names were Infinity and Beyond. I think they missed out. So in this case, you have two spacecraft, and instead of always doing the line of sight measurement, which requires you to be on the near side of the moon, they measure the change in velocity between the two spacecraft. So even though this spacecraft is on the far side and it can't see Earth, it can see the other spacecraft, and you can measure the velocities this way. And so that's the GRAIL mission. GRAIL stands for Gravity Recovery and Interior Laboratory. This was launched back in, I think, 2011, and it was a very short mission. It got to the moon, it orbited for less than a year, and then they intentionally crashed it into the surface of the moon. Here's again some schematics of it. The GRAIL mission was operated out of several different institutions, but the main one was MIT, and this is the principal investigator is Maria Zuber, who's really an outstanding scientist, and there's actually an article in the Smithsonian magazine if you are curious about what it takes to run a mission and do all this science while also dealing with politics, dealing with NASA. It's a great article. So they proposed this mission. It flew back in 2011. It had a set of objectives that are down here, but basically, even though I know you can't read it and you really shouldn't bother, it was to measure what you can't see from orbit, measure the interior of the moon, try to figure out how those volcanoes formed, how the big impact craters formed. Does the moon have a core? How big is that core? Since I've shown a lot of schematics of the spacecraft, here's some real pictures. Two little spacecraft, you can see people per scale, stacked into the top of a rocket, blasted off to the moon, and then they do these sorts of Doppler measurements. And so now I'm going to actually show some science, since I'm probably taking too long. Here's this animation. This is just to give you perspective where you're on the moon. And it measured the gravity field of the moon to ridiculous precision. To give you comparison, just back. Ooh, choo-choo, Doppler effect. Listen. Keep. Choo-choo.
He knew.
Come on,
Bloody engineers.
Okay, gravity. Connect to gravity. So this is the gravity field of the moon. The color variations represent very subtle variations in the surface gravity. So if you were to say to walk over the red region, you'd be pulled down slightly more. If you were to walk over the blue regions, you'd be pulled down slightly less. And by how much and how less this is about, again, these are variations. You wouldn't even feel this if you were there. These are of order of centimeter per second, or yeah, about 1,000th of a meter per second squared. Very small measurements. But the important thing, the fact I want to impress on you, is because of this mission, for the moon, we have the moon's gravity field as derived by GRAIL is the highest resolution global gravity field of any object in the universe.
Including the Earth?
Including the Earth. We have better gravity for the moon than the Earth. Why is that? This is a good question. I'll do this as my last question. Why do you think we can measure the gravity field of the moon better than the Earth? You've already... Yeah. No water? Not quite correct.
The moon's not tectonically active anymore.
Not quite. It's not tectonically active. Not because of the mantle. No, there's still radio interference. We have stuff here. What are you breathing? You're breathing in atmosphere.
The atmosphere from gravity.
The atmosphere does affect gravity, but not in the most obvious way. So you're dealing with spacecraft orbiting the planet, right? On the moon, you can have your spacecraft orbit 2 kilometers above the surface.
Right, or that far.
And it doesn't care. On the Earth, if you do that, you'll be on fire. Basically, because you can get closer to the surface, you can get higher resolution gravity. And so you can learn all sorts of really small scale stuff that you can't do on the Earth. we'll skip ahead. I have so many GIFs. But we'll look at some interesting things.
Is that how close to?
No, this isn't. These aren't to scale. I throw in. So this is a map of the.
No, the two. 2 years. Is that how?
2 kilometers. The GRAIL spacecraft orbited on average about 5 kilometers above the surface.
Wow.
Until the end, when it orbited about 0 kilometers above the surface. But yeah. So some interesting things to look at in gravity, just to highlight some of the science that's come out of this mission. One is impacts. How do impacts work? The Earth was created by impacts, yet, I mean, we're lucky here in Arizona, there's one just a couple hours north of us, but all the big impacts have been erased by plate tectonics. They're all gone. On the moon, they're all preserved. So we can look at these guys. This is a big impact crater. It's called Oriental. It's on the edge of the moon. You can only barely see it on the best of days from Earth. And we knew it's this big giant impact basin. And thanks to GRAIL, we can measure what's going on beneath the surface. And we'll actually skip ahead to another pretty graphic, I know. This is a plot of the surface of the moon. So again, we normally, if you have a spacecraft orbiting and it's not doing gravity, this is all you see. But if you have gravity, you can actually effectively peer beneath the surface and figure out the structure of the basin. So we know now that the centers of basins are thin. Basically, it's very thin crust there. The impact actually is excavated material and threw material out. And that material was deposited just outside the basin, so you get sort of thicker crust right around the basin. And so this is giving insight into how basins work on the moon directly, but this is also what happens on the Earth, and we can use this as an analogy to figure out how the heck basins work on the moon, on the Earth.
So the red would indicate that it was actually compacted?
So the red here means it's gravity high. This region is compacted. It's been melted, compacted, but it's also been fractured. So it's this whole mess of melty stuff. So other cool things. Getting back to that near side of the moon, I said I'd talk about the volcanoes. So again, this view isn't quite what you would see if you were looking at Earth. It's a little bit too far northward. But if you look, you can sometimes see the bunny. There's the ears and the head and the body. We knew for a long time that those were topographic lows. They were depressions, basins. Basically, the lava filled in the lowest lying regions. And we also knew something, that they were very oddly enriched in radioactive elements. But we didn't quite know where all this lava came from. Why is it all on the near side? And for the longest time, people thought that it was a big giant impact basin, just like the other one I showed you, except on a much bigger scale. Like maybe this is the circular rim of a basin that smacked into the moon a long time ago. But one of the biggest results that came out of GRAIL is it is not actually a big giant impact basin that made all the rabbit on the moon. And the way we know that is if we look at GRAIL and we look at the gravity data. This is the same region. You can see the impact basins that are on top of it. But you see this interesting border going around the edge. And if I do some magic, someone said magic, we can take a gradient of the gravity, and you see, again, this sort of odd feature. The weird thing is that is a square. You don't often see squares in nature, but it happens to be one, to within a few percent. These are corners. And basically, the idea is that these are rift valleys. On the Earth, in tectonic regimes, you sometimes get basically big giant rifts that then break off into triple junctions. You get 60-degree angles in some big faults on the Earth. The idea is that this is such a big scale that you actually have to worry about the curvature of the moon. And those 60-degree angles end up, these are actually 60-degree angles. It's just that the moon is so big that they look like 90 degrees in view from far away. You start making squares. But basically, I'm getting sidetracked with all the cool geometry. GRAIL discovered that the edge of all the dark stuff you see on the moon are big giant rifts. And so this is a little illustration that someone at NASA Goddard made up. Basically, early on in the moon's history, the moon actually fractured, that whole region melted. That's what helped produce that region. Not a big giant impact like we thought.
So had enough internal tectonics to create all that structure.
Yeah, so that ties into that map of all the thorium. It's basically, we think that all this radioactive elements that are on the near side of the moon, they were enough to heat up the near side of the moon and melt that region, and also drive all the tectonics associated with it. So I know it's probably gone too long, but so for a few minutes. So I'll close on this last bit. All the stuff we talked about so far is sort of right on the surface, like impact or in the near surface, the top 10, 20, 50 kilometers. GRAIL also has the opportunity to probe all the way down to the core of the moon, which almost no other technique can do. With the one exception of seismology. Seismology is the single best way to figure out what's inside of a planet. That's how we know the interior structure of the Earth to ridiculous precision, how we know we have a core, a liquid outer core. And the Apollo astronauts in the Apollo program, they were wise enough to place seismometers on the moon. And that gave us a lot of information, but all the data, they only collected data for a few years. And so, I already asked my question. Oh, I got one more. Eventually, we stopped getting data from the Apollo seismometers back in the 1970s. So my last question is, why did we stop getting data from the Apollo seismometers? Way back in there. You know the joke. We turned them off. So that was not a great move in NASA's history. Basically, we had a great working science experiment, but higher ups were worried about cost overruns with Apollo. So let's just turn off the science experiment. Needless to say, it'd be like turning off your TV, except your TV's on the moon, so you can't really turn it back on. So we don't really have great seismic data on the moon. GRAIL provides one additional way of probing it, and thanks to GRAIL, we know now that the moon has a solid core like the Earth, but it's also surrounded by a liquid outer core like the Earth. That core is much smaller than proportionally compared to the Earth's core with respect to the moon, the Earth's core with respect to the Earth. And so that tells you something about the two planets, or two bodies. I'm a planetary scientist, and I often say everything is a planet. Sorry, you're welcome, Pluto. So I often say that the moon is a planet. We have more data on the moon by a long shot compared to many planets. But thanks to gravity, we can do all sorts of things. We can probe the near surface of the moon. We can figure out tectonics that are beyond the reach of other orbital data sets, and we can go all the way down to the core. And so, even though the GRAIL mission is done, we actually had the last science team meeting last week, and they're officially out of money to do all the science analysis with. But because they were basically transformed lunar science, and the good thing is our gravity field is so good, we never have to go back and measure gravity of the moon. So instead, we'll go into some other planets. So I guess with that, I'll close. I took probably way too long. Oh, I'm fine. So, questions, if anyone has questions. We saw your So the question was, there's a solid and a liquid core, is there a magnetic field? There is no substantial global magnetic field right now. There are little pockets of magnetic fields, but like if you went to the moon, you had a compass, it wouldn't do anything. Which is odd. We don't really know a whole lot about the magnetic field of the moon. And it's one of the reasons, there's a few proposals in to send a spacecraft back to specifically measure the gravity field of the moon at really low altitude. So, yeah. Why did we crash GRAIL into the moon? We ran out of fuel. So basically the normal mission was to orbit like 10 kilometers above the surface. We did that. But to get the really high resolution stuff, you want to go as close to the surface as you can. And doing that, I mean, there's no atmosphere, so you can literally graze the surface of the moon. But you have all these fun little gravity anomalies tugging on your spacecraft in different directions. And then you need fuel to counterbalance that and correct your orbit. And eventually you'll run out. And so they ended up purposely picking a couple locations, and they impacted the spacecraft onto the surface of the moon.
And no seismometers to.
No seismometers to measure it.
How accurate were the early outset gravity measurements?
How accurate were the early, which,
Outset.
Alce,
Apollo, Luna,
so ALSEP didn't directly measure the gravity. It measured, ALSEP was seismic, and they also had the retroreflectors. Oh, the gravitometers. Oh, those have, no, I have not heard people talk about that data set in a long time. They may be accurate, but again, they're point measurements at on the near side of the moon where we had good data. And actually, now that I'm thinking about it, so they did measure, I think if I recall, they did traverses, but the noise in the data from astronauts lugging them around was sort of limits their usefulness. So they are not, we don't actually use that data set today, and I don't know if anyone's looked at it in a while. It'd be useful, it'd be interesting to look at it. Yeah, it's not the best, wasn't the best then, compared to today. Other questions? Back there. Yeah. No, yeah, you.
Do you know anything about the chemical differentiation between the layers on the inside of the moon?
Chemical differentiation between the layers of the moon. We do, and GRAIL has helped a little bit in that. Basically, the idea with the moon is, we think the moon formed after a big giant impact from the Earth, so big Mars-sized thing smacked into the Earth, threw off all this junk, and then accreted together and melted. And so it started, we call this the lava ocean, or magma ocean hypothesis, that the upper regions, or maybe the entire moon started molten. And as the moon cooled, different crystals, different mineral compositions froze out at different times. And then they, like you freeze out, ooh, Doppler? Come on, train. Oh. So we do know, and that's based, a lot of the magma ocean hypothesis is based on return samples, so we could bring back samples for chemical analysis, study them in big fancy equipment that we have on campus. GRAIL really helps with doing density measurements. So we know, for example, that the crust is actually lower density than we thought, which has important implications for that hypothesis on how things froze out. But there are still parts of that we don't understand, like why were all the radioactive elements on one side of the moon? Still an outstanding question. Okay, so with that I'll close. You can find me after.